All right, so in order to calculate that force, we need to get the acceleration of the ant. And the acceleration is going to be the acceleration due to the rotation plus the acceleration of the pivot point. And that acceleration of the pivot point is the acceleration of the truck. The acceleration due to the rotation, that's the one where we assume that the pivot is fixed. So that's the same one we've used for the other part. So this is going to be 0, negative 2.38 meters per second squared. But we have to calculate this one. So what's the acceleration of the truck? Well, you could think of it as a constant acceleration problem where you know TF, you know the initial velocity in x, you know the final velocity in x, and you're trying to calculate the x component of the acceleration. So 0 VFX is equal to 25 plus A times 1.5. So A is equal to negative 1.66? 16.6 meters per second squared. That's the x component. And so the acceleration of the pivot is negative 16.670. Any questions about that? So that's not the total acceleration, but that's the acceleration of the pivot point. And now to get the total acceleration, we're going to add that to this one. So the total acceleration is 0, negative 2.38 plus negative 16.670. And you get an acceleration vector of negative 16.67, negative 2.38. Any questions about that? And so now we have to use Newton's second law. We still have the weight going in, the normal force coming out, and then we still just have this horizontal friction force. And that's the only force in our coordinate system. So Newton's second law says FF, x and y components, is equal to the mass of the ant, 0.001, times negative 16.67, negative 2.38. And so for the force, you get negative 0.016, sixes all the way after, and negative 0.00238. So this is kind of maybe going overboard, fleshing this out, but so what was the difference here between this and the last example? Why, in this case, why did we get a different force? And in the last example, we got the same force as when the record player was still? Yeah, it just has to do with whether there's acceleration of the pivot point or not. Okay. Here's another example of the kind of problem that you'll have to do on the practice problems. So let's say that a centrifuge is accelerated from rest to 20,000 RPM over a time interval of 30 seconds. And we want to know first, what's the angular acceleration? And second, during those 30 seconds, how many revolutions does it make? So looking at this, do you have any idea what equations to use to solve something like this? So this is the kind of problem where you're going to use those analogs of the constant acceleration equations. Okay, so the three equations that you're going to use are omega f is equal to omega initial plus alpha t final. And then theta f is equal to theta I plus omega I tf plus 1/2 alpha tf squared. And then the last one is 2 alpha times theta f minus theta I is equal to omega f squared minus omega I squared. And the way to do it is just list out the variables you know, the variables you want. Yeah. And find one of these equations that has the variable you want and everything else is known. I guess the first thing we have to do is we want to convert everything to SI units. So again, we're going to go from rotations per minute to radians per second. So 20,000 rotations per minute. One rotation is 2 pi radians. And 1 minute is 60 seconds. And so you get an angular velocity of 2,094.4 radians per second. Okay, so let's just go through all the possible variables and see what we know. Do we know either of the two angular positions? Well, you might as well always just say that your reference position is the position, your reference orientation is the orientation when time is equal to 0. So theta I is just going to be equal to 0. Theta final, we don't know. Do we know omega initial? The angular velocity initial? Yes. So it's starting at rest, so that's 0. Do we know the final angular velocity? Yep, that's the one that we just converted. So 2094.4. Do we know the angular acceleration? $30, right? No? Okay, we don't know that then. I knew it was either 30 or we didn't know it yet. Okay, so is there, and then T final, do we know T final? Oh yeah, that one's 30. So any of these three equations have alpha and then everything else is known? Yeah, the first one. So 2094.4 is equal to 0 plus alpha times 30. Solve that and you get alpha is equal to 69.8 radians per second squared. And then for part B, we still know all the stuff we knew before. And now we also know alpha is 69.8. And what are we looking for? Well, the idea is we're going to look for theta final, get a number of radians, a huge number of radians, and then we're going to convert from radians to rotations because every 2 pi radians is 1 rotation. Okay, so looking for theta final. So this time, what equation do we want to use? Yep. So theta final is equal to 0 plus 0 plus 1/2 times 69.8 times 30 squared. And you get a value of 31,410 radians. But that's not rotations. So now we just have to convert 31,410 radians to rotations where 2 pi radians is 1 rotation. And you get a value of 4,999.1. That's got to be round off. It must be 5,000 for some reason. Rotations. Any questions about that? Okay, so now what's the acceleration of a point in the centrifuge ten centimeters from the pivot at the instant just before the angular acceleration ends? We can choose any point. I guess let's choose a point over here. This is the pivot. This is 10 centimeters. Let's say that it's going counterclockwise. Well, what two things do we have to calculate to figure out the total acceleration at that point? Yep, centripetal and tangential. What direction is centripetal? Yep, so there's the centripetal. What direction is the tangential? Downward, right. So the velocity is this way, right? And it's speeding up, so tangential has to be that way. Any questions about that? And now we need to get the magnitudes. The centripetal acceleration magnitude is v squared over r. R is 0.1. So we need to figure out the speed of that point. So what equation do we use to get the speed? So the equation for the speed is the one that relates the angular velocity to the speed, this one. Magnitude of the velocity is equal to the absolute value of omega times r. Omega, at just the instant before that acceleration stops, omega is 2094. .4. The radius is 0.1. So that speed is equal to 2009.4. And so the centripetal acceleration is 209.44 squared divided by 0.1. Can someone calculate that? $651 meters per second squared. And so the centripetal acceleration vector, we know it's pointing in the positive x direction, so that's positive 438, 651, 0. The tangential acceleration, we know its magnitude is equal to the absolute value of the angular acceleration times r. We calculated that angular acceleration is 69.8. R is 0.1. So this is 6.98 meters per second squared. We know the tangential acceleration is pointing in the negative y direction. And so the total acceleration of that point is 438,651 negative 6.98 meters per second squared. Any questions about that? So there are really, I guess, 5 equations that you're going to need to deal with for the practice problems in the exam. Those 3 constant acceleration equations that are analogous to the, to the translational, those 3 constant acceleration translational equations. And then the 2 that relate translational quantities to rotational quantities. Okay, that's this one for tangential acceleration and this one for speed. Okay. Next week, I'm planning to have basically the same office hours that I usually have. One difference, I put this on D2L, is as long as nobody has any major complaints about it, I'm planning to do my Monday and Wednesday office hours from 2 to 4 instead of 4 to 6. But I also, we don't have classes next week. I'm just going to be grading and stuff. So if you want to meet outside of those times, just send me an email and we can definitely find a time that we can meet. Okay. All right. Thanks for being in my class.